Welcome to the course on design of power electronic converters. We were discussing IGBTs. So, we had seen some basics of IGBTs and then we also saw the switching characteristics of IGBTs. Now, let us look into some of the datasheet notations that are given in the IGBT datasheets. So, some of the important notations are, first is your maximum collector emitter voltage. So, this is the maximum voltage that the IGBT will be able to withstand. So, IC is the collector current and VCE is the collector emitter voltage. So, the maximum voltage that can this device can block is your this VCES, and then when it is in saturation, that means it is in the on state, then there what will be the drop across it, what could be the typical value or the maximum value, that is your VCE on, collector to emitter saturation voltage. Then is your IC, which is your maximum DC collector current. That means if we continuously keep on passing current through it, then based on the temperature, what could be the maximum collector current that can flow, that is your IC. And ICM is the maximum pulse collector current. This I have discussed before also in case of diodes and also in case of MOSFETs. So, when you give this kind of a pulsating current, your IC that we can give or the device can withstand can be much greater than your this IC DC continuous current rating, but this time period may be very short. Okay. So, that is your maximum pulse collector current. And then there can be some leakage current also while this is blocking. So, at that time ideally it should be 0, no current should flow, but there is always some current that keeps on flowing. So, that is your leakage current, which is denoted as your ICS, collector to emitter leakage current. Then what could be the gate emitter voltage, VGE, that is your gate to emitter voltage. Then what could be the threshold voltage, which is the minimum voltage that you require for this part to drive this IGBT and for it to start conducting. So, that is your threshold voltage. Then forward transconductance, this we had discussed before what it is. So, that also is usually provided in the data sheets. Then is your gate to emitter leakage current. Over here also we may be having some leakage current flowing while ideally when there cannot be any current. So, that is your gate to emitter leakage current. Then let us look into some of the performance curves. So, first one is your output characteristics of an IGBT. So, this is between your collector current IC and your collector to emitter voltage VCE, and it depends on changes with how much gate to emitter voltage we apply, and also it can be different depending on the temperature. So, here what you see is that this is for 11 volt and then for 15 and 17 volt it is provided. So, if we give more than 11 volts, like if we give around 15 volt, that is when it goes over here, which is your saturation region, and that is what we want in power electronic circuits, for it to go into the saturation region. Then this is your transfer characteristics, typical transfer characteristics, which is a graph between your VGE, gate to emitter voltage, and your collector current IC. So, you can see here that till at this point more than 5 volt there is no current. That means this is the threshold voltage, and then after that it starts to increase, the collector current starts to increase beyond this gate emitter voltage. So, then after that further it increases lot. So, that is your, and the slope of this line is your forward transconductance GFE, and this also curve can be different based on the temperature, it may vary this transfer characteristics. Then notations related to switching, I have shown this before in the last lecture also. This is just for the sake of completion, I wanted to show you again that your total gate charge, then gate to emitter charge is provided in the data sheets, then gate to collector, so Miller charge, then your turn on delay time, what it is we have seen during the study of the switching characteristics. Then the rise time, that is usually defined as the time between when the collector current rises to 10% of the maximum value at IGBT turn on, and when collector to emitter voltage drops to 10% of the maximum value. Okay, so that is like a sum of the rise in current and the fall in voltage. Then TD off, turn off delay time, and fall time TF corresponding to the turn off, that is your collector current dropping from 90% to 10% of maximum value. Then your input capacitances, output capacitances, reverse transfer capacitances, these are also usually mentioned in the data sheet. Plus apart from that, in IGBT data sheets they also provide E on, E off, that is your switching loss, turn on switching loss, turn off switching loss, and the sum of these two, which is your total switching loss. Now one more performance curve which is of great importance is your gate charge characteristics. So this is between your gate charge and your VGE. So usually for your IGBTs a negative voltage is given to turn it off. So let us say if this started from minus 8 volt, then initially when the charge increases, this VGE decreases, it becomes 0, and then further it increases and reaches to this point, which corresponds to your Miller voltage. So this corresponds to your Miller voltage. So Miller voltage, and then further what happens is that after the Miller period is over, which is over here. So this is when our Miller period gets over. After that, whatever is the leftover voltage, which because it has to, the gate emitter voltage has to match with the driver's voltage, gate driver's voltage. So that is what I mean it goes up to, and whatever is the charge associated with that, it charges also accordingly. So this is basically, this region is associated with your charging of the gate to emitter capacitance, and this Miller part is mostly associated with your gate to collector being charged, which also acts as the Miller capacitance, and then further again it is the gate to emitter which gets charged after this point over here. Then others are your other curves that may be provided are your these losses, switching losses versus your gate resistor RG. Now this gate resistor plays a very important role, because if we increase the gate resistor, then the turn on and turn off time increases. So then correspondingly what we observe is that as we increase the gate resistor, what we see, the turn on your losses, that is increasing a lot, you can see over here. Whereas your turn off losses, switching losses, they are not increasing so much, and this is your diode reverse recovery loss, ERR. So this one is associated with your diode. So that also we do not see much change, in fact a slight decrease also is observed as your gate resistance RG is increased here. And this is then how these switching losses they change with your collector current IC. Now what we expect is that as your collector current increases, then your turn on and turn off times obviously are going to increase. And so here we see that your this E off and your E on both are increasing as your collector current is increasing, and that is what is expected. But we do not see significant change in the diode losses, the turn off loss or the reverse recovery loss that is associated with the diode. Further in the data sheet, your turn on times and turn off times, how they vary with RG and the collector current, that also is many times provided. So, this is the graph between your RG, this RG gate resistor and your turn on and turn off times. So, what we observe here is that the delay time, delay on time and delay off time, they also slightly increase with the gate resistor. Turn on time, this rise time TR is increasing significantly with the increase in gate resistor. Fall time, there is not much significant change with the change in gate resistor. Then further, when we observe how these turn on turn off times vary with collector current, what we see is that this TD off time delay in during the turn off reduces little bit. On TD on, delay during for the turn on is not much affected. The TF time for turn off is also not much affected, but however the rise time that increases with the collector current. So, what are the key points of this lecture? That the important notations in your data sheets related to IGBTs are your blocking voltage and the current carrying capacity, current ratings. You can look into the DC continuous rating and also the pulse current rating. And also you should be looking into the on state voltage drop or the saturation voltage drop. Further, you should be also noting down the characteristics and the notations and the values related to switching and the different performance curves that may be given associated with them. And also look into the gate to emitter voltage, what is the threshold voltage and what is the typical voltage that you should apply to turn on the IGBT. Thank you.